Today we will talk about limits which involve infinity in one way or another, and geometric representation of such limits, which are lines called asymptotes. First, we define what it means for a function to have a limit as x approaches infinity. Then we go over several useful techniques which allow us to calculate limits at infinity. Then we investigate the global behavior of functions and whether their graphs approach asymptotes, vertical or horizontal. Limits at infinity describe the long-term behavior of functions. That is, what happens as x gets really, really large, positive or negative. Sometimes the function will approach a specific number as x gets large. This number is called the limit of the function at infinity. To be precise, limit of f of x as x approaches infinity equals L means that the values of f of x can be made as close to L as we like by taking any x which is sufficiently large. Similarly, limit of f of x as x approaches negative infinity equals L means that the values of f of x can be made as close to L as we like by taking any x which is sufficiently large negative. As an example, consider function f of x equals x minus 2 divided by the square root of x squared plus 1. We can look at the graph to investigate its behavior for large x. We see that as x grows larger and larger, the values of f of x get closer and closer to 1. It appears that the limit at infinity of f of x exists and equals to 1. On the other side, for large negative x, the graph appears to converge to negative 1. So we conjecture that the limit of f of x when x approaches negative infinity exists and equals negative 1. It is important to understand that the limits we found by looking at the graph may be wrong. Here are two reasons why. First, we are only seeing the values of f up to x equals 10. So perhaps at x equals 15, f makes a steep ascent or descent away from 1. Of course, we can graph it for larger x, say up to x equals 100. But then again, we do not know what happens at x equals 105. Continuing with this argument, we can never be sure that our answer is correct or that f even has a limit. Second, even if we know that the function is slowly increasing, we may not be able to precisely determine the value it is approaching. Here it could be 0.99 or 1.1 or anything else in the neighborhood of 1. To reliably determine limits at infinity, we need to develop an algebraic approach. The starting point is to investigate limits as x approaches positive and negative infinity of the function 1 over x. If x is large, say greater than 100, then 1 over x is less than 1/100th. When x gets larger, say x is greater than 10,000, then 1 over x gets even smaller, specifically smaller than 0.0001. For instance, for x equals 62,708, which is greater than 10,000, 1 over x equals 1 divided by 62,708, which is approximately 0.001594, which is less than 0.0001. So when x is large, 1 over x is small. In fact, by taking x large enough, we can make 1 over x as small as we like. Therefore, according to the definition, the limit of 1 over x as x approaches infinity equals 0. Similarly, limit of 1 over x as x approaches negative infinity equals 0. Because when x is large negative, 1 over x is small negative. For instance, let's take x equals negative 10,000. Then 1 over x equals 1 over negative 10,000, which is negative 0.0001. This is a small negative number, close to 0 on the left. The graph of y equals 1 over x is a hyperbola. We see that the curve approaches the value y equals 0 when x is large positive and large negative. It can be proven that the limit laws and the squeeze theorem are valid when x approaches a is replaced by x approaches infinity or x approaches negative infinity. Applying the product law repeatedly to the limits from the previous example, we obtain that for any positive integer n, limit as x approaches infinity of 1 over x to the n equals 0, and limit when x approaches negative infinity of 1 over x to the n equals 0. Using this important rule and limit laws, we are able to calculate limits at infinity of rational and some irrational functions. Our first example is to evaluate limit as x approaches infinity of 2x plus 1 divided by x minus 2. Notice that when x gets large, the top 2x plus 1 gets large and the bottom x minus 2 gets large. So we cannot immediately tell what the behavior of the function is as x gets large. We can think of this as a competition between the numerator and the denominator. Both are getting larger and larger, and the question is, does one of them outstrip the other? Or do they stay about even as they get larger? In order to figure this out, we need to use the following technique. Divide the numerator and denominator by the highest power of x in the denominator. So here we divide the top and bottom by x. Let's divide term by term. On the top, 2x over x gives 2 plus 1 over x. On the bottom, x over x is 1, so we get 1 minus 2 times 1 over x. We use limit laws and evaluate the limit of each term. 2 is a constant, so it does not change. 1 over x tends to 0 as x approaches infinity. In the denominator, 1 is again a constant, and 1 over x tends to 0. So the limit is 2 divided by 1, which is 2. So we can conclude that the numerator and denominator stayed about even as they grew larger. This is because the highest power of x in the numerator is the same as the highest power of x in the denominator. The second example is to evaluate the limit as x approaches infinity of 2x cubed minus 5x plus 1 divided by 4x cubed minus 7x squared plus 2. To evaluate the limit at infinity of any rational function, we first divide both the numerator and denominator by the highest power of x that occurs in the denominator. In this case, the highest power of x in the denominator is x cubed. So we divide the numerator and denominator by x cubed. We divide each term and obtain 2 minus 5 times 1 over x squared plus 1 over x cubed divided by 4 minus 7 times 1 over x plus 2 times 1 over x cubed. We use limit laws and compute the limit of each term separately. In the numerator, 2 is a constant, so limit of 2 is 2. Since 1 over x to the n approaches 0 at infinity for any n, here for n equals 2, we get that 1 over x squared goes to 0. The same is true for 1 over x cubed. When x approaches infinity, 1 over x cubed approaches 0. In the denominator, 4 is a constant, so it stays. But 1 over x and 1 over x squared go to 0 at infinity. We obtain that limit equals 2 over 4, which is 1/2. Therefore, the limit at infinity of this rational function is 1/2. Notice here that nothing would change if we decide to compute the limit as x approaches negative infinity, because 1 over x to the n approaches 0 when x gets larger, positive or negative. So exactly the same calculation shows that the limit as x approaches negative infinity of this function is also 1/2. Our next example is to evaluate limit as x approaches negative infinity of x squared plus 4 divided by 2x minus 5. Since it is a rational function, we divide the numerator and denominator by the highest power of x in the denominator. Here the highest power of x in the denominator is 1. So we divide the numerator and the denominator by x. We obtain x plus 4 over x in the numerator and 2 minus 5 over x in the denominator. When x approaches negative infinity, 4 divided by x tends to 0, and 5 divided by x tends to 0. Now we see that the denominator approaches a number 2. However, in the numerator we have x, which tends to negative infinity. So here we have a large negative number divided by 2, which is again a large negative number. Therefore, the limit is negative infinity. In this case, the numerator outstripped the denominator. This is because the highest power of x in the numerator is greater than the highest power of x in the denominator. The fourth example is to evaluate the limit of x cubed minus 2x. When x is large, both x cubed and 2x are large, and it is not clear what happens to their difference. When x approaches infinity, x to a power can only get larger, so x cubed approaches infinity. 2x also approaches infinity. So if we look at what each term is doing in the limit, we obtain an infinity minus an infinity. We are probably tempted to say that the answer is 0 because we have an infinity minus an infinity. But we would be wrong. Infinities do not behave as real numbers. when it comes to arithmetic. Without more work, there is simply no way to know what an infinity minus an infinity might be. Here, both terms have a common factor x. Factoring out x, we obtain x times x squared minus 2. X approaches infinity, and x squared minus 2 also approaches infinity, because when x is large, x squared is even larger, and negative 2 will not make much of a difference. Thus the product becomes arbitrarily large, and the limit is infinity. The fifth example is to evaluate the limit as x approaches infinity of square root of x squared plus 1 minus x. Again, when x is large, both the square root of x squared plus 1 and x are large, so it is difficult to say what happens to their difference. To compute the limit, we need to rewrite the function. Let's multiply and divide by the conjugate, x squared plus 1 plus x. Then in the numerator, we get the difference of squares, and the denominator stays the same. The square root and square reverse each other, so we obtain x squared plus 1 minus x squared divided by radical x squared plus 1 plus x. In the numerator, x squared cancels with negative x squared, and we get 1 over square root of x squared plus 1 plus x. Notice that the denominator of this expression tends to infinity, because x approaches infinity, and then we add another very large number, the radical of x squared plus 1, which is also approaches infinity. Since the denominator increases without bound and the numerator is a constant 1, the limit is 0. The last example is the one we used to initiate our discussion of limits at infinity at the beginning of this lecture. We will evaluate limits at positive and negative infinity of the function x minus 2 divided by square root of x squared plus 1. Recall that we used the graph of this function and conjectured that the limit at positive infinity is 1 and the limit at negative infinity is negative 1. Now we will compute these limits algebraically to see whether our conjecture is correct. Again, here both numerator and denominator get large as x gets large. From the previous examples, we learned that in such case we divide the top and bottom by the largest power of x in the denominator. However, there is a square root in the denominator, which makes things more complicated. If we look at the expression under the radical, the highest power of x there is x squared. Let's try to factor out x squared from under the radical and see what happens. Under the radical, x squared plus 1 equals x squared times 1 plus 1 over x squared. Since the radical of a product equals the product of the radicals, we get in the denominator square root of x squared times square root of 1 plus 1 over x squared. Recall that the square root of x squared equals the absolute value of x. So we obtain the following expression: x minus 2 divided by the absolute value of x times the square root of 1 plus 1 over x squared. Absolute value of x behaves differently for positive and negative values of x. That's why limits at positive and negative infinity will be different. When we compute the limit as x approaches positive infinity, we only consider large positive values of x, and thus we can simply drop the absolute value here. For positive x, the absolute value of x equals x. Now we divide top and bottom by x and simplify. We get 1 minus 2 over x divided by square root of 1 plus 1 over x squared. 2 over x tends to 0 at infinity. 1 over x squared also tends to 0 at infinity. Thus the limit is 1 over square root of 1, which is 1. Now let's look at the limit at negative infinity. When x is a negative number, the absolute value of x equals negative x. So we replace the absolute value by negative x. Then, as before, we divide the numerator and denominator by x and simplify. We obtain 1 minus 2 over x divided by negative square root of 1 plus 1 over x squared. As x approaches negative infinity, 2 over x tends to 0, and 1 over x squared tends to 0. So the limit equals to 1 divided by negative square root of 1, which is negative 1. Our conjecture based on graphical data was correct. Limit at infinity of this function is 1, and limit at negative infinity is negative 1. Notice that the limits at positive and negative infinities are different. The reason is the radical in the denominator. This cannot happen if your function is rational, that is, a quotient of two polynomials. In the case of rational functions, limits at positive and negative infinities are the same. Horizontal asymptotes describe the long-term behavior of a function, that is, what happens to the values of f of x when x becomes increasingly large positive or negative. The line y equals b is called a horizontal asymptote of the curve y equals f of x if either limit of f of x at positive infinity equals b or limit of f of x at negative infinity equals b. Let's go back to our previous example and consider f of x equals x minus 2 divided by the square root of x squared plus 1. We computed that the limit as x approaches positive infinity of this function is 1, and the limit as x approaches negative infinity is negative 1. Therefore, lines y equals 1 and y equals negative 1 are horizontal asymptotes. Graphically, asymptotes of a function are usually represented by dashed lines. On the graph, you see two dashed horizontal lines, y equals 1 and y equals negative 1. When x grows larger, the graph of the function sort of flattens out and gets closer and closer to the asymptote. Let's find horizontal asymptotes for function 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. To do that, we simply need to compute limits of f at positive and negative infinities. Let's start with the limit as x approaches positive infinity. Since f is a rational function, we need to divide the numerator and denominator by the highest power of x in the denominator, which is x squared here. Let's divide top and bottom by x squared term by term. We obtain 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. Now, 1 over x tends to 0 at infinity. 2 over x squared also tends to 0. In the denominator, 4 over x approaches 0 and 1 over x squared approaches 0 at infinity. What we have left is 3 over 5. So the limit equals 3/5. Since the limit as x approaches infinity is 3/5, the line y equals 3/5 is a horizontal asymptote. Notice that nothing changes in the computation if we replace infinity by negative infinity. Therefore, the limit at negative infinity is also 3/5, and function approaches the line y equals 3/5 at both infinities. We can see on the graph that the curve gets closer and closer to the horizontal line y equals 3/5 when x increases to positive infinity and when x decreases to negative infinity. Now let's find horizontal asymptotes for function sine x divided by x. When x approaches positive or negative infinity, the sine function itself continues to jump up and down. The limit of sine x at infinity does not exist because of oscillation. However, the limit of sine x over x at infinity exists and equals 0. Here is the reason why. The sine of a really big number must still be somewhere in the range of -1 and 1, while denominator will simply be a really big number. Therefore, the quotient turns out to be small. We prove it here using the squeeze theorem. For any x, sine x is between -1 and 1. Let's consider positive x first. Then we can multiply this inequality by 1 over x. When x approaches positive infinity, 1 over x tends to 0. Therefore, the lower and the upper bound of the function 1 over x sine x approaches 0 at infinity. The squeeze theorem guarantees that in this case the middle function must also approach 0. So by squeeze theorem we obtain that limit as x approaches infinity of sine x over x equals 0. Therefore, y equals 0 is a horizontal asymptote. Limit at negative infinity is the same because, and you can check that, sine x over x is an even function and is therefore symmetric for positive and negative x. On the graph, we see that even though the function oscillates indefinitely due to the sign in its numerator, the amplitude of the oscillation gets smaller and smaller, and therefore the graph gets squeezed towards the x-axis, which is its asymptote. We are also interested in vertical asymptotic behavior, where the function value f of x approaches positive or negative infinity. The line x equals a is called a vertical asymptote of the curve y equals f of x if either the left-hand limit of f of x at a is plus or minus infinity, or the right-hand limit of f of x at a is plus or minus infinity. As an example, consider function f of x equals 1 over x minus 2. Let's compute one-sided limits of f at 2. When x approaches 2 from the left, x is smaller than 2, and thus the denominator x minus 2 tends to 0, staying negative. The left-hand limit is negative infinity. When x approaches 2 from the right, x is larger than 2, and the denominator x minus 2 tends to 0, staying positive. The right-hand limit is positive infinity. Therefore, the line x equals 2 is a vertical asymptote. The graph of f of x is a shifted hyperbola. You see that the graph decreases to negative infinity along the line x equals 2 on the left and increases to positive infinity along the line x equals 2 on the right. Let's find the vertical asymptotes of tension x. Recall that tension x equals sine x over cosine x. One of the points where the denominator cosine x equals 0 is pi over 2. Let's compute one-sided limits at pi over 2. The left-hand limit of tension x at pi over 2 is the left-hand limit of sine x over cosine x at pi over 2. Since sine x is continuous and sine of pi over 2 is 1, the numerator tends to 1. Cosine x is positive when x is less than and close to pi over 2. Therefore, the denominator approaches 0, staying positive. So the limit is positive infinity. The right-hand limit of tension x at pi over 2 is the right-hand limit of sine x over cosine x at pi over 2. Again, sine is continuous, and that pi over 2 has value 1. Therefore, the numerator tends to 1. Cosine x is negative when x is greater and close to pi over 2. Therefore, the denominator approaches 0, staying negative. So the limit is negative infinity. The line x equals pi over 2 is a vertical asymptote. Since tangent has period pi, we can obtain other vertical asymptotes by adding pi to pi over 2 or subtracting pi from pi over 2. We obtain vertical asymptotes at 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, and so on. Generally, lines x equals pi over 2 plus pi n for integer values of n are the vertical asymptotes of tangent x. If you look at the graph of tangent x and concentrate on the line x equals pi over 2, you see that tangent increases to positive infinity on the left and decreases to negative infinity on the right. Our last example is to find all asymptotes, horizontal and vertical, of rational function f equals 2x squared plus x minus 1 divided by x squared plus x minus 2. Let's start by finding horizontal asymptotes. We need to compute limit at infinity of 2x squared plus x minus 1 divided by x squared plus x minus 2. The highest power of the denominator is x squared. So we divide each term of the numerator and denominator by x squared and obtain 2 plus 1 over x minus 1 over x squared divided by 1 plus 1 over x minus 2 over x squared. In the numerator, 2 is a constant. 1 over x tends to 0 at infinity, and so does 1 over x squared. In the denominator, 1 is a constant, but 1 over x and 1 over x squared tend to 0. Therefore, the limit is 2. Also, when x approaches negative infinity, we can repeat the same calculations and obtain 2. Therefore, y equals 2 is a horizontal asymptote. This behavior is typical for rational functions. They have the same horizontal asymptote at positive and negative infinity. To find vertical asymptotes, we find zeros of the denominator. We solve x squared plus x minus 2 equals 0 for x, either by factoring or using quadratic formula. We obtain two roots, x equals negative 2 and x equals 1. The denominator factors as x plus 2 times x minus 1. We will compute one-sided limits of f at negative 2 and 1. The left-hand limit of f at negative 2 is the limit as x approaches negative 2 from the left of 2x squared plus x minus 1 divided by x plus 2 times x minus 1. The numerator is continuous, and thus to find the limit value of the numerator, we plug in x equals negative 2 into 2x squared plus x minus 1. We get 5. In the denominator, when x approaches negative 2 from the left, x is less than negative 2. So x plus 2 approaches 0, staying negative. X minus 1 tends to negative 3 at negative 2. So in the denominator, we have a small negative number times negative 3, which is a small positive number. So the limit is positive infinity. Let's compute the right-hand limit of f at negative 2. Again, the value of the numerator at negative 2 is 5. X minus 1 at negative 2 is negative 3. X plus 2 at negative 2 is 0. But since x approaches negative 2 from the right, x plus 2 approaches 0, staying positive. Comparing the signs, we see that the limit is negative infinity. Now we compute one-sided limits at 1. In the left-hand limit of f at 1, the value of the numerator at 1 is 2. At 1, x plus 2 equals 3, and x minus 1 at 1 is 0. Since x approaches 1 from the left, x minus 1 approaches 0, staying negative. Therefore, the limit is negative infinity. Similarly, when x approaches 1 from the right, the value of the numerator at 1 is 2, The value of x plus 2 at 1 is 3. X minus 1 at 1 is 0. But since x approaches 1 staying greater than 1, x minus 1 tends to 0 staying greater than 0. Therefore, the limit is positive infinity. We have two vertical asymptotes, x equals negative 2 and x equals 1. Let's use the information we collected about the asymptotical behavior of f of x to sketch its graph. Y equals 2 is a horizontal asymptote at positive and negative infinity. We indicate this by drawing a dashed horizontal line at 2. Function has two vertical asymptotes, x equals negative 2 and x equals 1. We draw two vertical dashed lines at negative 2 and 1. We computed the left-hand limit at negative 2 to be positive infinity. Thus, when x approaches negative 2 from the left, f increases to positive infinity. So the graph has to look like this. It approaches the horizontal asymptote at negative infinity and increases to positive infinity along the vertical line x equals negative 2 from the left. The limit of f as x approaches negative 2 from the right is negative infinity. So the graph has to decrease along x equals negative 2 on the right. We know that the graph goes from point 1/2 on the y-axis because f of 0 equals 1/2. The limit of f as x approaches 1 from the left is negative infinity. So the graph should go downwards along the line x equals 1. The limit of f as x approaches 1 from the right is positive infinity. So the graph should start at infinity on the right of the line x equals 1 and then approach the horizontal asymptote y equals 2. Here we have a graph of f of x equals 2x squared plus x minus 1 divided by x squared plus x minus 2. This is the end of our lecture.